In this lesson, we discuss extreme values of functions on closed intervals. Now, when we talk about extreme values, we mean maximum or minimum values of a function. We're going to use the idea of a derivative in order to find these extreme values. Let's start with the definition. Here we have the definition for what it means to be an absolute maximum or an absolute minimum. So first, we have a function whose domain is D. F is said to have an absolute maximum value on that interval D, or on that domain D, at a point C. So C is where the absolute maximum is located. If you can show that f of C is really greater than or equal to f of x, I'm reading that from right to left, for all x in that domain, and has an absolute minimum value on D at C, so C is where the absolute minimum is located, if f of C is less than or equal to f of x for all x in the domain. And we mentioned that maximum and minimum values are called extreme values of the function. Absolute maxima is plural for maximum, or absolute minima, that's plural for minimum, are also referred to as global maxima or minima. I would like you to consider the graph of y equals x squared over different domains. And the idea of this example is that the domain has a lot to do with whether or not the function has absolute maxima or minima. And so let's first consider the graph of y equal to x squared over the domain of all real numbers. So if I can quickly draw just a rough sketch of all real numbers, the graph of y equals x squared over all real numbers, it would be this, right, folks? And so what I want to show is that there is no absolute maximum because this function never stops increasing. So there is no maximum. We do not say that infinity is the maximum because maximum or minimum values, extreme values, are real numbered values. So what real number is the maximum? There is no real number that's the maximum, so there is no maximum. However, there is an absolute minimum, and the minimum is located at x equal to 0, and that minimum value is 0. I would like to stress just one little thing here. The actual minimum value is 0. It's located at x equal to 0. In other words, when you're like at this point right here, 0, 0, right at the origin, this x value, that's where the minimum is located. The function value, the real numbered function value, is the actual minimum value. So this is where the minimum is located. This is the minimum value. All right. Now let's change the domain. Let's consider the graph of the function y equal to x squared, but over the domain 0 to 2 only. So basically from 0 to 2, well, let me alter our graph really quickly, and then we can answer the question. So let's see if I can draw this really quickly. From 0 to 2, this would be 4, and then this is 2. All right, cool. So then the graph of y equals x squared only from 0 to 2 is this graph here. And so on this, notice that this interval here is closed. It's closed. The previous example, all real numbers, that was an interval that was not closed, right? It went from indefinitely in both directions. This interval here was not closed. This one is closed on both ends. It's closed. It's a closed interval. And in this case, when it's closed, we do have a maximum a maximum up here and a minimum. We have both a maximum and a minimum over this closed interval. So our absolute maximum is 4, and it's located at x equal to 2. The minimum is 0 at x equal to 0. All right, now what happens if we have this interval? It's open on the left, but it's closed on the right, okay? Let's see what we have. So basically, I think I could probably keep my picture, can't I? The only difference is right here at x equal to 0, we're going to have to keep that open like that. All right, there's the graph. How does that change the existence of extreme values? Well, notice that because it's not a completely closed interval, we would have to say, yes, there's a maximum, but there's no minimum. All right, so we have an absolute maximum value of 4 at x equal to 2, but no absolute minimum. All right, finally, let's look at when the interval is an open interval. So all I have to do, folks, is change this, right? That right there, let's change that to being open like this. There, cool. So what that changes for us is that now there's no maximum and there's no minimum. We can just say there's no absolute extrema. Extrema meaning there's no maximum and there's no minimum. So I hope that you see that it was only over this closed interval where we had both a maximum and a minimum. So we have this theorem called the extreme value theorem. It says that if f is continuous, that's the first condition, it has to be continuous, on a closed interval, that's the second condition, then we know for sure f will attain both an absolute maximum and an absolute minimum. Okay, they're calling the absolute maximum capital M and the absolute minimum value m, lowercase m. But what's really important is that we note the conditions, right? F must be continuous and the interval must be closed. Then you can guarantee both an absolute maximum and a minimum. Now, what's very important to note is that if a function is not continuous, then we cannot guarantee the existence of both an extreme, both absolute maximum and an absolute minimum, okay? But if a function is continuous on a closed interval, we can guarantee, there must be an absolute maximum and a minimum, all right? Now, these are just different graphs, different sketches. I just drew them really quickly to show different ways that we can have an absolute maximum occur or an absolute minimum occur. So here, notice this is I didn't mean to spell maximum that way. Oh, let me fix that. There's not two x's in maximum. All right, got it. This is a maximum at this point here. It's called an interior point because it's not one of the endpoints. Okay, this is not an endpoint. So it's an interior point. This is a minimum value, and it's also at an interior point because it's not an endpoint. This is a maximum, and it's located at an endpoint, a minimum at an endpoint. This is a minimum at an endpoint, but a maximum at an interior point, a minimum at an interior point, and a maximum at an endpoint. So notice that maximums or minimums can occur at an endpoint or an interior point. That's really important. All right, very good. What I want to do is look at a new definition for us, and it's going to be the definition for what we mean for a local or relative maximum, a local or relative minimum. So here is the definition for a local maximum, a local minimum. A function f has a local maximum value at a point C within its domain D if f of c is greater than or equal to f of x for all x in D lying in some open interval containing C. You have a local minimum at C if f of c is less than or equal to f of x for all x in D. Here's a picture to kind of go with the words here. This picture is to help us identify types of maxima or minima. Okay, now first of all, notice that this function is defined on this interval from A to B. All right, there's your interval from A to B. Notice that A is your endpoint, B is your right. A is your left endpoint, B is your right endpoint. All right, this value here at the endpoint is an absolute minimum. It's considered an absolute minimum because it is the smallest function value on the entire interval. There's no smaller value of f anywhere. It's also considered a local minimum, okay? Because any function value nearby this value will be greater than or equal to this value here. Okay, so another way I can say that differently. For every value nearby, right, in the neighborhood, this value here is the least of all. Okay, so it's also a local minimum. So in other words, if you're an absolute minimum, you're also a local minimum. This is a local maximum because in the neighborhood or anywhere near this point, right, there's no greater value of f nearby. That's why it's called a local maximum, sometimes also called relative maximum. Now, this point is not an absolute maximum because there's a larger value on the interval between A to B. You know what I mean? It's not the greatest of all, but in this neighborhood, if you will, it's a maximum. So this is a local or relative maximum. Here's a local minimum. It's not an absolute minimum because there's a lower point over here, but it is a local minimum. It's the smallest value of f nearby. Here's a local maximum, but it's an absolute maximum because there's no greater value of f anywhere, not just nearby, but anywhere. And then finally, this is a local minimum, no smaller value of f nearby. I didn't mean to capitalize f right here. I'm still talking about the same function. All right. Please notice that C, E, and D are all interior points. C, E, and D are interior points. A and B are not interior points. Those are endpoints. Now, what we're going to be asked to find are these points, these extrema. And notice where they're located, everybody. Notice that right here, the derivative is the line let me see if I can make some room. There we go. Notice the line tangent to the curve here is horizontal. That means the derivative here is equal to 0. Same thing goes for the line tangent to the curve here at that local minimum. The tangent line is horizontal. Here, notice that the derivative of action, because of this cusp right here, the derivative does not exist. It's not differentiable here because of this cusp. So where will I may be getting ahead of ourselves a little bit here, but I just want to take advantage of this picture to show you that we're going to be able to find our extrema by finding where the derivative is 0 or where the function is not differentiable. So this theorem here just follows from what we were just noticing, is if f has a local maximum or minimum value at an interior point C, so I'm talking about like right here, of its domain, and f prime is defined at that interior point, then the derivative must be 0. So this is an interior point, so is this, right? There's a maximum here, local maximum, there's a local minimum here, and notice that the derivative is equal to 0 here. The derivative exists here, it's defined, and it's defined here. It's not defined here because of that cusp. But if the derivative exists, if it's defined at that interior point, and you have extrema, then the derivative has to be equal to 0. The line tangent to the curve at that point, at that extrema, is horizontal. So let's see if we can summarize what we're saying here. These are the possible locations for a function to have an extreme value, either local or global, okay? First, any interior point where f prime is equal to 0, that's where a function can possibly, okay, not for sure, but possibly have an extreme value, okay? or any interior points where f prime, the derivative, is undefined. It's possible for the function to have an extreme value there. Or at any of the endpoints of the domain of f, right? If I scroll back up here, if I can, there we go. If I scroll back up here, folks, notice, look here, where are the extrema located, the local and global? Well, there's one here that's an endpoint, one here at the endpoint, right? So at endpoints, right here where the derivative is equal to 0, okay? And right here where the derivative is not defined. Again, it's not defined there because of that cusp, right? So that's why we're saying, if I could come back here, we're saying that the only places where a function can possibly, that word possibly is important. We're not saying for sure there's an extreme value here, but it's possible to have an extreme value at these three locations where the derivative is 0, that's the horizontal tangent line. The interior points where f prime is undefined, so f prime would be undefined like at a cusp or a corner or something like that, or at the endpoints of your domain. An interior point of the domain of a function f where f prime is 0 or undefined is a critical point of f, okay? So this is very important. A critical point, first of all, is an interior point of the domain. A critical point is an interior point of the domain where the derivative is 0 or undefined. So, again, I'm sorry, but I'm going to scroll back up, okay? These would be in critical points, right here. C would be a critical point. Why? Because, first of all, it's an interior point, and the derivative is 0. This point E would be a critical point because it's an interior point and the derivative is 0. This point here, D, would be a critical point because it's an interior point and the derivative would be undefined. A and B, even though that's where extrema are located, those are not called critical points because they are not interior points, they are endpoints. Okay, so C, E, and D are examples of interior points. Excuse me, critical points. All right, very good. Now, once again, I just want to, I think it's worth stressing and saying again, let's make sure we don't misunderstand what we're saying here. Just because you're a critical point doesn't mean there's a local extreme value there, okay? What we are saying that is if you know if there's an extreme value, right, then that point is a critical point for sure. But just because you're a critical point doesn't mean that there's an extreme value there, okay? The critical points are possible locations for extreme values. Said another way, critical points are good candidates for extreme values. All right, so because we're going to be asked to find extrema, these are some steps that you can follow to find them. First, find all critical points because their critical points are good candidates, right? Possibilities for where extrema are located. So find all the critical points. And the critical points will be located where the derivative, here it is, where the derivative is 0 or where the derivative is undefined. Okay, then you're going to evaluate the function at all those critical points and the endpoints. Don't forget the endpoints because that's an absolute maximum or a minimum can occur there as well. Take the largest and smallest of these values. All right, cool. So let's look at an example. All right, check it out. We have the function f of x equal to x squared. This is for sure continuous, we know that. And we have a closed interval, -2 to 1. So again, remember that as long as the function is continuous on a closed interval, then we know that we have an absolute extrema. They must exist, right? All right, so we know we can find it. All right, folks, so let's go for it. The first thing we're going to do is find our critical points, okay? In order to find the critical points, you're going to have to find f prime, okay? F prime of x, the derivative of x squared, is equal to 2x. Now, what we need to do is we need to find where f prime is undefined. Now, this function is differentiable over its entire domain. So your f prime will never fail to exist. F prime will never be undefined because this function x squared is differentiable over its entire domain. Therefore, the only critical point occurs when f prime is equal to 0. That is to say, when 2x is equal to 0, which of course means when x is 0. X equal to 0 is your one and only critical point. Okay? Now, what we need to do is we need to evaluate our function at our critical point and the endpoints, all right? So I like to go in order, folks. You don't have to. So f of -2, I need to evaluate f at 0, and I need to evaluate f at 1. I want to be clear. -2 is an endpoint. 0 is my critical point. 1 is an endpoint, all right? So here we go. F of negative. We're evaluating the function, the original function, okay? We're not evaluating f prime. We're evaluating our original function at these values. So then this is -2 squared, which is equal to 4. This is 0 squared, which is 0. And then this is 1 squared, which is 1. So then this is the greatest value, and this is the smallest value. So therefore, the function has an absolute maximum value of 4 at -2. It has an absolute minimum value of 0 at 0. Let me write that down for us. All right, cool. I hope that was straightforward, and I hope it was clear. Let's look at a brand new function. And it's going to be the same quest or same task. Find the absolute maximum and minimum values. All right, find the absolute maximum and minimum values. We could have just said find the extrema. Okay, that would have been shorter. Find the extrema of this function. Now, this is a polynomial function, so we do know it's continuous over its entire domain. And so it's continuous, and this is the closed interval that we're being asked to consider. So by the extreme value theorem, we do know that extrema exist. All right, so here we go. F prime of x, the derivative function, is equal to 8 minus 4x cubed. Now, remember, this function is a polynomial function, so it is differentiable over its entire domain. So therefore, like the previous example, the only critical points will occur when the derivative function is equal to 0. That is to say, when 8 minus 4x cubed is equal to 0, which implies that 4x cubed is equal to 8, which implies that x cubed is equal to 2, which implies x is equal to the cube root of 2. This is our one and only critical number. Let's make sure this falls within the domain. The cube root of 2 is positive. We want to make sure that, so it's for sure greater than -2. Is it less than 1? No, right? It's not. Because the cube root of 1 is 1. Therefore, the cube root of 2 is greater than 1. This falls outside of this domain. You know what that tells me? That the absolute extrema must occur at the endpoints then. I mean, because we know they must exist. And this is the one and only critical point, and it's outside of this domain. So that disqualifies this from being an absolute extrema. So then all we need to do now then is to evaluate our function at the endpoints. I'm trying to create room here. So f at negative 2. So this is 8 times negative 2 minus negative 2. Watch your signs to the fourth power. So then this is negative 32, right? Because this is negative 16 minus 16, so negative 32. And then f of 1 is equal to, when you substitute 1, it basically is just, it just amounts to you adding the coefficient. So it's 8 minus 1. So then this is 7. All right, very good. So then this must be your minimum, and this is your maximum. All right, cool. Let's look at another function. All right, here we're given a function x to the power of 2/3 on the interval from negative 2 to 3. All right. First things first, find the derivative function. All right, here we go. F prime is equal to, this is the power rule, so it'll be 2/3 times x to the power of 2/3 minus 1, which is equal to 2/3 times x to the power of negative 1/3. So then this is equal to 2 over 3x to the 1/3. So this is the derivative function. Okay, now listen, folks. The critical points are located where the derivative function is equal to 0 and or where the derivative function fails to exist or where it's undefined. This derivative function is undefined if x is equal to 0. Okay, and x equal to 0 is an interior point. So then 0 is a critical point. Now, is this ever 0? Well, this is only 0 when the numerator is 0, but the numerator is fixed at 2. So then this function only has one critical point, and that's at 0. So what we're going to do is we are going to evaluate our function at our endpoints and also at 0. So let's do that now. So I'm going to do f. Remember, you're evaluating f, okay? At negative 2, you'll evaluate f at, let me see if I can move this up, okay? F at 0 and f at the right endpoint of 3. Okay, so then this is negative 2 raised to the power of 2/3, right? So this is, the cube root, I'm going to rewrite it like this, okay, of negative 2 squared. That's what these rational exponents mean. So it's the cube root of 4. This is 0 raised to the power of 2/3. So it's the cube root of 0 squared, which is just 0. And then you have 3 raised to the power of 2/3. So then this is the cube root of 3 squared, or the cube root of 9. Out of all of these points here, this is the largest, and this one is the smallest. So the function has an absolute maximum of the cube root of 9, which is approximately, 2.08, okay, approximately, at x equal to 3, and has an absolute minimum of 0 at 0. Awesome.